Okay, so in order to actually find a size threshold for the number of edges required, basically, for there to be a Hamiltonian cycle, we need to first do some playing around with the algebra situations, particularly a combination theory. So remember you have NCR is just equal to n factorial n minus r factorial r factorial. So if we look at what NC2 is just going to be n minus 1 divided by 2. Or more specifically, when we actually go and put it in, we have n factorial, n minus 2 factorial, 2 factorial, and we can rewrite our n factorial as n minus 2 n factorial times n minus 1 times n, and then we can have the n minus 2 factorial there, and the 2 factorial, we can then cancel that out, and that's what gives us this n minus 1 divided by 2 situation. Another aspect we can go ahead and play with is n minus 1c2 is going to be equal to n minus 1 n minus 2 divided by 2. How does that work out? Again, taking that original formula, you have n minus 1 factorial, n minus 1 minus 2 factorial, 2 factorial, and we can go ahead and firstly rewrite that as n minus 3 factorial, which means we want the top one to be represented with the n minus 3, so which means we can extend that, so we have n minus 3 factorial multiplied by n minus 2 multiplied by n minus 1 all over n minus 3 factorial, 2 factorial, so that cancels with that, and 2 factorial is just 2. So we have this coming from this piece here, and we have, this coming from this piece here. Okay, so if we know that, so we've just taken our combination formula, and we've written NC2 in terms of it, simplified, and n minus 1C2 simplified. Now we can go on to a theorem that is going to be useful to us. Okay, so now we're going to look at a theorem which is just going to help us to the theorem that we're actually interested in. So this one is a case of NC2 is greater than or equal to n minus 1 C2 plus 2 for n greater than or equal to 3. Now, just a reminder of what this is actually saying. It is saying that we have n minus 1 upon 2 is greater than or equal to n minus 1 n minus 2 divided by 2 plus 2 for n greater than or equal to 3. Okay, which means we want to somehow get to these two pieces. So we're going to start off with this proof by actually just starting off with n greater than or equal to 3 and using algebraic manipulation, or algebra basically, to get to the point where we have these combinations occurring. So we're just going to start off with n greater than or equal to 3. So the very first thing we're going to do is we're going to say, okay, let's multiply both sides by 2. So we have 2n greater than or equal to 6. Now, the idea behind both sides is we have quadratic equations, or because we have n minus 1, n times by n minus 1, and n minus 1 times by n minus 2. So we have an n squared situation occurring. So we're going to go, okay, fine, let's add n squared to both sides, because that, again, doesn't change anything then. So we add n squared to both sides, and we get n squared plus 2n is greater than or equal to n squared plus 6. And then again, just a reminder, it is because we have n times by n there and n times by n there. Okay. Next up, we again want a quadratic formula situation, And ideally, we want a quadratic formula which ends up with n minus 1 coming out there. And comes out with n minus 1, n minus 2 coming out there. So now we look at how exactly can we get there. So how exactly can we get there? Well, at the moment we have, if we look at this, we have n, and we have n plus 2. Obviously, that's something we don't really want. We want n minus 1. So how can we get to that point? Well, we want minus 1. We currently have 2n. So what can we do here to get to that point? Is we can subtract 3n from both sides. Because if we did that, we subtracted 3n from both sides, we would end up with n squared plus 2n minus 3n, and that would give us, n squared minus n, which gets us to the n minus 1. And if we do it on the other side as well, we have n squared minus 3n plus 6. And there, if we factorize it now, we will have n minus 1, n minus 2. But in that case, we have a leftover. So let's actually just discuss that a little bit further, actually. So we do it on the one side, we get the n minus 1. We still have it's greater than or equal to that. And we have, right now, this n squared minus 3n plus 6. But we want to get down to n minus 1, n minus 2. What we have to do there, and again, I'm just going to remove this. What we have to do here is we want n squared minus n minus 2n plus 2, which gives us n squared minus 3n plus 2. So we can get that out if we just add additional 4 on the outside there. So again, just to note, so we did the one time, we're like, oh, well, how do we get to n squared minus n? Because that's, we want to end up with n minus 1. We said, okay, well, we can just subtract 3n on that side and 3n on the other side. Then we're like, okay, on the other side, we want to get n minus 1, n minus 2. And when we play around with that, we notice we can get to this part here, which is incorporated in what we already have. So with just like a leftover piece. So we can rewrite that. So we say n squared minus 3n plus 2 plus 4. Then we have, this n minus 1 coming out. We have that n minus 1, n minus 2 coming out, plus 4. Now we just need to go through our process and be like, okay, well, we need to divide by 2. So let's divide both sides by 2. So we divide both sides by 2, and we get n minus 1 divided by 2 is greater than or equal to n minus 1, n minus 2 plus 4 divided by 2. And you can rewrite this second one as 2 separate, n minus 2 divided by 2 plus 2. And therefore, you now get what we originally wanted out. So we know that nc2 is greater than or equal to n minus 1 c2 plus 2. And we're going to use this in the proof that's actually worthwhile to us. Okay, so now we're actually at the theorem which gives us a threshold value for the size to guarantee that it is a Hamiltonian graph. So the theorem is, let G be a connected graph of order n, where n is greater than or equal to 3, then if the size of G is greater than or equal to n minus 1 c2 plus 2, then G is Hamiltonian. So when we're doing this proof, like all the proofs that we've done with Hamiltonian, we notice we can put it into two cases. either the graph is complete, and if it's complete, it is Hamiltonian, and we're pretty much sorted. We just have to make sure that if it's condition A, which is the size of the graph is greater than or equal to n minus 1 C2 plus 2, or we look at the case where G is not complete. So let's start off with the easier case. If G is complete, okay, if G is complete, then the conditions of the theorem hold. Theorem hold. In other words, the size of G is greater than or equal to n minus 1 C2 plus 2. What exactly is n minus 1 C2 plus 2? Well, you can think of it as just when you have a complete graph, you have nC2 is greater than or equal to n minus 1 C2 plus 2. So in that case, the conditions of the theorem hold purely because in the complete graph, it's nC2. But we also know, and this is what we need to write now, is we also know Kn is Hamiltonian. So if it's complete, we know the size is greater than n minus 1 C2 plus 2 because we know that nC2 is greater than that. And we also know that the complete graph is Hamiltonian, so we're done. Then we look at case 2, if G is not complete. So if G is not complete, we're going to have a pair of non-adjacent vertices. So we're going to have, a U of V, which is not an element of the edge set. What we're going to do here is we're just going to give you an example here. You have A, B, C, D, and you have this kind of a situation. We are looking at a pair of vertices which is not an element of the edge set, so like B, C. And we're saying, let's create a new graph. Let's create a graph H where we take away those vertices. So we have a graph H, which is actually going to be a D in this example case. But we're looking at, we have original G, and then we have G minus, your BC. So we're going to do that. So we're going to say, let H be equal to the original graph minus the two vertices where the vertices were non-adjacent pairs of vertices. So we subtract that. And then we say, okay, what we have here is that we have the size of our original graph is equal to the size of our smaller graph plus the degree of the vertice that was removed plus the degree of the other vertice that was removed. And again, that kind of makes sense because when we removed it, we removed, the degrees of those vertices. So we have the size of this graph plus the degree of the vertice here and the degree of the vertice there. And we think to ourselves, okay, at this point, so because we introduce size, then we think to ourselves, well, we want to show that it's Hamiltonian, and now we suddenly go, this is something that we've seen before. We've seen that the degree of U plus the degree of V of the non-adjacent vertices, if we can show that this is greater than or equal to n, then we have Orr's theorem being satisfied, and then we know that the graph is Hamiltonian. So that's what we're trying to end up with. But we need to actually get it to be greater than or equal to n, which means we need to rewrite the size of H and the size of G in something that we can write in terms of n. Now, we have a condition for G, because we said the size of G must be greater than or equal to n minus 1 C2 plus 2. So we know this. So we can say, we know that the size of G is greater than or equal to n minus 1 C2 plus 2. Then we have to think of, okay, what about the size of H? Now, the size of H is going to be smaller than the size of the complete graph in terms of the H. What I mean by that is, we know that a complete graph size nC2, right? But now we've moved two vertices. So we pretend for a second that, the graph that we had was complete. We moved two vertices, and then we have n minus 2 C2. But we know that wasn't complete to begin with. So we now know that the size of H has to be smaller than or equal to n minus 2c2. Okay, so that's just coming from, we know that the size of a graph, if it's a complete simple graph, is nc2. We remove 2 vertices from the original graph, which is of order n, so we have that n replaced with n minus 2, so we know that it is going to be smaller than that. That's what we know for definite. Okay, so if we know that for definite, we know that the size of G, written in terms of this n minus 1c2 plus 2, we know that it's greater than that number. So we know n minus 1c2 plus 2 is going to be smaller than the size of H plus du plus dv. But we also know that the size of H is less than n minus 2c2. So when we go ahead and replace the size of H with n minus 2c2, we can say n minus 1c2 plus 2 minus n minus 2c2 is going to be less than or equal to du plus dv. Okay, and now we get to just play around with substituting in our combination formulas and hope that it shows us that it's greater than or equal to n. Okay, before we continue, I just want to make du and v on this side. So it's du dv is that side greater than or equal to n minus 1c2 plus 2 minus n minus 2c2. Remember in our combination formula, which is NCR is equal to n factorial, n minus r factorial, r factorial. We're going to rewrite this combination formulas in. So we're going to have n minus 1 factorial, n minus 1 factorial minus 2 factorial. I did put a factorial in the wrong place there. 2 factorial plus 2 minus n minus 2 factorial, n minus 2 minus 2 factorial, 2 factorial. Okay, so let's just simplify this a bit. N minus 1 factorial, n minus 3 factorial, 2 factorial is just 2. We have 4 over 2 plus, well, minus n minus 2 factorial, n minus 4 factorial, all divided by, that's a very bad factorial sign, 2. Okay, so now we get to try and simplify things out. So we have n minus 3 factorial on the top, n minus 2, n minus 1, plus 4, minus, and we just expand n minus 2 factorial, n minus 3 factorial, 2 divided by 2 there, n minus 4, n minus 3, so minus 4 factorial, n minus 3, n minus 2, n minus 4 factorial, 2. We can then cancel out, that there and that there. And that gives us, again, we have n squared, and I'm just multiplying everything out now. So n squared minus 3n plus 2 plus the 4 that's there minus n squared minus 5n plus 6, but this is all minus divided by 2. Okay, and if we do that, we're now going to get minus 3n plus, where does the plus come from for that minus over there? So that becomes a minus, that becomes a plus. So we have 2n situation happening there. So we have 2n coming out. Our n squared cancels with our n there. We have plus 2 here, plus 4 year minus 6 years, that cancels out. Everything divided by 2. We could have written all of this as equals, just by the way. And when we do this, that's equal to n. So we have that du plus dv is greater than or equal to n. Where does the greater than or equal to sign come into play? Because it was over there. And the rest are all equal to, so everything is greater than or equal to. And therefore, by Orr's theorem, it is Hamiltonian. So we have a threshold of size where once it reaches that size, it's guaranteed to be Hamiltonian.